Graphing systems of inequalities. So we're going to sketch the solution set for the system, and then we're also going to indicate whether the region is bounded or unbounded. So we're going to pretend these are lines. So in your mind, you're going to think, okay, this is x plus y equals 5, y equals x plus 1, and y equals 6. You're going to do more and more and more of these, and you're going to be able to do this without having to write this step, but for now, let's write it. So if you notice, this first one is in standard form, ax plus by equals c. X and y are on the same side of the equation. So a fast way to find a point on this line, points on this line are to find the intercepts. Okay, so remember when you're finding x-intercepts, you set y equal to 0. When you're finding y-intercepts, you set x equal to 0. So I want you to set x equal to 0, which means this piece right here is gone. Because when x is 0, that whole term disappears, right? So then you can just look at the equation and you can solve it from there. When x is 0, what's y? Well, y is 5. We're going to do the same thing with y. If we want to find the x-intercept, we're going to set y equal to 0. So cover it up with your finger. You set y equal to 0, it's gone. Pretend it isn't there. Then you see that x is 5. So we have 5, 0 here. Okay, now look at the next equation. We have y equals x plus 1. You can do lots of things here. You could go ahead and find the x and y intercepts in the same way, so let's do that. So if x is 0, we're looking for the y-intercept, but if x is 0, I can cover it up with my finger and it's gone, right? So if x is 0, what's y? We'll pretend that piece isn't there. Y is 1. Let's do the same thing. Now let's let y be 0. Y is 0, this side is gone, it's 0. So this one's a little more complicated. We have 0 equals x plus 1. We need to solve that for x, so we can subtract 1 from each side. So we see x equals negative 1. So when y is 0, x is negative 1. Remember, my points go x, y all the time. Well, we know y equals 6 is a horizontal line, 6 units above the x-axis. I do want to point out that the line y equals x plus 1 is in slope-intercept form. Y equals mx plus b form. You could also plot the intercept, which is 0, 1, and then using the slope. But let's go ahead and do it with these intercepts. Another thing you may have noticed is that I did not give you a grid. There's no XY axes, there's no scale, you don't have anything to start with. And that's what's really cool about this. You're going to have to get to figure out, whichever way you think about it, what an appropriate axis system is. So we want the XY axis, but how many tick marks? What's our scale going to be? So let's look at our numbers. We have 5 for x and y, that's the maximum we have of the points. And we have y equals 6 for this horizontal line. Okay, so we always want to make sure we go just a little bit bigger than our max. Okay, so let's go 7 in either direction on the positive x and positive y. Look at the values here. Which one's the smallest? Well, we have a negative 1 for an x, so let's go negative 2 for the x and the y as well. So this is a rough sketch. I don't expect yours to be perfect. We're just looking at the basic premise of this. Now we're going to plot our points. So for x plus y equals 5, we're going to plot 0, 5. 1, 2, 3, 4, 5. And 5, 0. So let me label a few of these tick marks. 2, 4, 6. 2, 4, and 6. Okay, so we're going to plot 5, 0. And if you notice, the first equation, x plus y equals 5, would be the line, but we had greater than or equal to as our inequality. So if you have an equal as part of the inequality, then you're going to draw it with a solid line. Okay, we're going to label the line. The line is x plus y equals 5. When you label it, you're labeling the line, you use an equal sign. Okay, now we're going to look at the next one, y equals x plus 1. But if you notice, the original inequality was a strict inequality. Y is strictly greater than x plus 1. So we're going to use a dotted line here. This first one was solid because of this equal part. You notice the second one does not have that equal part, so we're going to put a dotted line. We're going to plot 0, 1 and negative 1, 0. And I'm going to draw it dotted. And look at the last one, y equals 6. We said that was a horizontal line, but we see it is also going to be solid because there's this equal part right there. And we really need to label each one. I forgot to label this one. I'm labeling them with an equal sign because I'm labeling the line. Okay, now we're going to figure out what the solution set looks like. So we're going to do our shading. Okay, so we're going to look at each one of them. I'll start with the top one. X plus y is greater than or equal to 5. We're going to choose a test point that is not on the line. I'm kind of lazy. I want to do something really easy, so I'm going to pick 0, 0 if possible. So I'm going to pick a test point that is not on the line. And I notice 0, 0 is not on my line. X plus y equals 5 was this green line right here. And notice 0, 0 is right here. We're not going to have 0, 0 crossing through that line. So we're going to plug in the test point, which means this x and this y. We're going to plug in x equals 0, y equals 0. We're going to see what happens. So if we plug x equals 0, y equals 0, we get 0 plus 0 is greater than or equal to 5. 0 is greater than or equal to 5. That is false. We are always going to shade the true. So that means we're going to shade the side without the point 0, 0. Remember, if you're shading a line in space, either this half plane is true or this half plane is true. So we're going to test one side of it and see what behavior we have. Okay, so we see that we're going to shade the side without 0, 0. So here's 0, 0, we're shading this way. Okay, I'm just going to draw some arrows for now for you to see. I'm shading like this. I may make them shorter in just a bit, but I'm shading all the way through like this. Okay, now we test the next line. So the next line is y is greater than x plus 1. So let's check that one out. Here's y equals x plus 1. Notice 0, 0 is not on that line. So I'm going to use the same test point because it's easy. I'm going to use my test point of 0, 0, which means x is 0, y is 0. So I'm going to replace y with 0. And I'm going to replace x with 0. So I see that 0 is greater than 1. Again, that's false. So I'm going to shade the true. So I'm going to shade the side without 0, 0. So that means here's 0, 0. I have to shade this side. Okay? So you're going to shade like this. Okay. And we have one more. We have y is less than or equal to 6. So again, here is y equals 6. Here's 0, 0. 0, 0 is not on that line. So it is appropriate for me to use 0, 0 as a test point. 0 is less than or equal to 6. Well, this time that's a true statement, right? I shade the true, so I'm going to shade the side of that line that contains 0, 0. So now I'm shading down like this. And I know it's kind of busy. I get that. So let's extend the pink arrows all the way. Okay, so we see everything up here is shaded. And look at the green here. So we know definitely, let's just do a piece at a time. If I shade above here, it's all this stuff, right? And then we shade the green, it's all this stuff. So let's look at that, those two pieces together. So we see so far, it's bounded by these pieces, right? That makes sense? Considering those two. So now we also look at that y equals 6, the horizontal line, and we're shading down from there. So I cannot look at this region up here above it. That doesn't make sense. That's not included. So you're going to see that we end up with this region right here. This is shaded for all three pieces. Okay. So we call this S. S is our feasible set. S. And notice I have 1, 2, 3. We're going to call them corner points. That's where my boundary lines intersect. And we say S is bounded because we can enclose S in a circle, completely enclose S in a circle. Okay.